Hey guys, today we're going to take a look at correlation, or the linear relationship between two variables. Let's start by looking at this cartoon with the angry statistician. He says we've ruined his positive association between height and weight. We're actually going to take a look at examples today, including height and weight examples, and we're going to look at a measurement for the correlation or association between two variables. Let's start with an example. Let's say we had the age and weight of a sample of 10 adults. We're actually going to create a scatter plot of the data below, and we're going to look at whether or not there is a relationship between the age and the weight of these adults. So to make a scatter plot, we're going to go to our Inspire graphing calculator, and we're going to enter this data in list and spreadsheets. If you need to pause the video and come back at any time, please feel free to do that. I've actually already filled out the list and spreadsheets on my calculator. So I have gone to my calculator and entered all the data for the age and weight of individuals. To create a scatter plot, we add a page. So I am going to go Control, Add a Page, and I'm going to add a Data and Statistics page. Now remember, this page reads everything that's in list and spreadsheets. I've actually pre-populated quite a number of charts, so I'm going to have a number of different variables here. You won't have all of those as you get started. So we click along the bottom of the x-axis to add our variable, and for this example, that's age. Our y variable was weight, so we're going to click the y-axis and select the weight variable. Well, from the scatter plot, it looks like that there is no linear relationship between x and y, or there's no association or relationship between an individual's age and their weight, which makes perfect sense. What about, though, if we looked at the height and weight of two individuals? So let's actually take a look at some data on height and weight. If I were to take a look at those same 10 individuals with the same weights, but now I associated their weight with their height, now we can take a look at whether or not there's a relationship between height and weight. Now, I'm going to go back to my list and spreadsheets. I've already got weight entered. The only thing I need to do is add a new column for height. So when I go back to my list and spreadsheets on my calculator, I now have data for both the height and weight of those individuals. I'm going to go to a scatter plot, and now my x-axis is going to be the individual's height, because it makes sense that your weight would be dependent on your height. So weight is our y and height is our x. So now we can look at the relationship between a person's height and a person's weight. Well, now there does appear to be a linear relationship between weight and height. So how strong is that linear relationship? Well, that's what we're looking at today when we study correlation. Generally speaking, when we talk about correlation, the closer the points in a scatter plot are to a straight line, the stronger the relationship is. That means, conversely, the farther away the points are from one another, the weaker the relationship. So if we look at these two examples again, closer points form a stronger or more linear relationship. More scattered points form a weaker linear relationship because they are further away from a straight line. Here are a number of different examples. If you notice in the top row, from left to right, our relationship gets stronger. All three of those are examples of positive relationships between x and y, but the closer the points are to a straight line, the stronger the relationship. The last graph here has a perfectly linear positive relationship because all of the points fall on a perfectly straight line. In the second row, we go from a negative to a strong negative to a perfect negative relationship between x and y. When all of my points are scattered at random, like in the bottom left corner, there are no relationships between x and y. And then this graph right here is very interesting. There is a very clear relationship between our x and y variables in our scatter plot, but it appears that that relationship is quadratic. Correlation just measures the linearity of the relationship between x and y. Since there is no linear relationship between X and Y, we would say that there is no correlation. All right, so let's take a look at some examples, and you're going to predict whether these two variables would have a positive, negative, or no association or correlation with one another. The first is the heights of mothers and the heights of their adult daughters. Generally speaking, tall mothers have tall daughters, so we would say there is a positive association. The age of a car in years and its current value. Generally speaking, the older a car is, the less value it has, so that would be a negative relationship. The weight of a person and the calories consumed. Well, generally speaking, the more calories you consume, the more you weigh, and also the more a person weighs, the more calories they need to sustain them, so that would be a positive relationship. The height of a person and the person's birth month. Well, it doesn't make sense to have any relationship between those two variables, so we would say no association. The number of hours spent in safety training and the number of accidents that occur. Well, I hope the longer you spend in safety training, the less accidents you have, so we would say there is a negative relationship. So we've been able to predict relationships and even look at scatter plots and determine whether the relationships are positive or negative, just like slope. But how do we really measure the strength of those relationships? That's where we have a value that comes in called our correlation coefficient, abbreviated with a lowercase r. Our correlation coefficient is a quantitative assessment, that means a number or a numerical value, of the strength and direction of the linear relationship between bivariate quantitative data. All right, let's break that down. Bivariate means two variables. Quantitative data means numerical data. So when we create a scatter plot, it's two variables, an x and a y, that are both numerical variables or numerical data. So we calculate correlation coefficients when we have bivariate numerical data, and the number that we calculate tells us the strength, which is either strong, moderate, weak, the direction, positive or negative, of that linear relationship. The one we use in this class and most often is called Pearson's sample correlation. Now, we're in a class called statistics because we do a lot of calculations based on samples that we use to infer something about a population. If we really had a population of data, then we would calculate a parameter for our correlation coefficient, abbreviated with the Greek character rho. What we generally have is our statistic, which is abbreviated with a lowercase r. Our correlation coefficient is calculated using this formula. Now don't worry, your calculator does the work for you, but it's probably worth noting how this formula is calculated. Notice if we look here at the first parenthesis, each x, we take every individual x and subtract the average of the x's and divide by the standard deviation of the x's. In the second column, we take each y value, subtract the average of the y's, and divide by the standard deviation of the y's. We multiply these values together, add up all of those products for all of the different x values, and divide by n minus 1. So our Pearson's correlation coefficient is based not just on the individual x values, but the average and standard deviation of x's, as well as the individual y values, their average, and their standard deviation as well. So let's actually take a look at a couple of examples so you can learn how to calculate this on your graphing calculator. Our first example is going to be looking at 6 data points where we're comparing the speed limit in miles per hour to the average number of accidents that occur every week. So we're going to look at what the relationship is between speed limit and average number of accidents. We're going to do that by calculating our R and then interpreting it in context. So if we go back to our graphing calculator, I have all of this entered in my list and spreadsheets. So I can go down to my speed and accidents. I've entered those data points in my calculator. And what we can do is actually add a page, just a normal calculator page, to do this calculation. So I'm going to go to a normal calculator page. I'm going to go Control Doc to add a page. I'm going to add a calculator page. And everything we do generally is under statistics. So menu, this class is statistics. We're going to do a stat calculation and we're going to do a linear regression, mx plus b. Our calculator is going to ask us what our x's are. In this case, they were speed. The calculator, this is a drop-down menu, so we click this arrow. It's going to ask us our y values. These were the number of accidents. And then all we have to do is toggle down and click OK. The calculator gives me my slope, my y-intercept, my r-squared value, which we'll discuss in another class, and my r value of 0.996359. Well, what does that r value mean? That r value tells me that there is a strong, positive, linear relationship between the speed limit and average number of accidents per week. The r value tells me it's strong. I'll show you how I know that. The r value was positive, as was the slope, so it's a positive relationship. The relationship is linear, and we're looking at a relationship between speed limit and average number of accidents per week. So how do we determine what's strong, what's weak, what's moderate? Well, let's take a look at all of the values that r, our correlation coefficient, can take. The correlation coefficient can be any value between -1 and 1 inclusive, meaning including those endpoints. If my r value is 0 or close to it, it tells me that there is no linear relationship between my variables. When I'm looking at the sign of the r value, whether it's positive or negative, the only thing that tells me is the direction of my relationship. Positive r values correlate to positive slopes. Negative r values correlate to negative slopes or negative relationships. So if my r value is between 0 and 0.5, either positive or negative, we say that that is a weak correlation between the x and the y variables. If my r value is between 0.5 and 0.8, or -0.5 and -0.8, that is considered a moderate correlation between my x and y variables. And finally, if my correlation is greater than 0.8, between 0.8 and 1, which would represent a perfect correlation where every point is exactly on a straight line, or between -0.8 and -1, again, -1 would be every point on a perfectly straight line, that would be a strong correlation between the variables. Now, there's several characteristics of our correlation coefficient that are important to discover. So we're actually going to do a little discovery with our calculator. We're going to start by looking at these values for x and y. We're going to enter the x and y values in our list and spreadsheets on our calculator, and we're going to calculate our r value. All of our x values are in millimeters. Once we calculate r, we're going to change them to centimeters and find r again. So I'm going to go back to my graphing calculator. I've already got this entered, so we are going to take a look at x and y. So we've got our x values and our y values. We're going to add a page, Control Doc. I'm going to add a normal calculator page, menu, statistics, stat calculations, linear regression. My x's are now called x. My y's were the y values, and we're going to calculate r. My r value is 0.918146. So we have a strong relationship between x and y. We want to see what happens now if we change our x value units from centimeters to millimeters. Well, to do that, if we go to our list and spreadsheets, we can create a new column. I'm going to call this x1. In my equals line, I'm going to tell the calculator to take all of the values that I already had in my A column, and I'm going to multiply those values by 10, which will convert from millimeters I'm going to divide by 10, sorry. We're going to convert those from millimeters to centimeters. Now, my calculator did all of the work for me because I entered this in my equals. I told the calculator to take column A and divide by 10. Now, these are in fraction form. That's not a problem at all. We're going to go back to our normal calculator page. We saw our R value from before. We're now going to do our linear regression again. Statistics, stat calculations, linear regression. We're going to tell the calculator to take the new x's, x1, and our y values. And here's the new correlation coefficient, 0.918146. So if you notice, changing the units on all of our x values did not change my correlation coefficient. What I simply did was divided all the x values by 10. If I multiply or divide my terms by a constant, my correlation coefficient will not change. Now let's take a look at what happens if we change what we call the independent and dependent variable. So we said x was our independent variable, y was our dependent variable in our data here. Let's switch that. Let's tell the calculator to switch our x and y, and let's see what happens. So again, I'm going to go to my normal calculator page, menu, statistics, stat calculations, linear regression. But now the calculator is asking where our x's are. Those are our inputs. I'm going to tell the calculator to use my column y. And my y's are my outputs or my dependent variables. I'm going to tell the calculator to use x. So I'm switching my input and my output here, and I click OK. My R value does not change. Now, certainly my equation for the relationship between the variables does, but my R value remains the same. So my correlation coefficient does not change when I change the independent and dependent variables or the input and the output. All right, the last thing I want to do now is take a look at what happens when we have an outlier. So we're going to go down to our highest y value, which used to be 12, and we're actually going to change that to a value of 22. I'm going to go back to my normal calculator page, and I'm going to calculate my R value again. Menu, statistics, stat calculations, linear regression. My x's are going to be x. My y's are going to be y. Now remember, this time I have actually changed my highest value for y. Now if you look, my R value is 0.626. It is significantly lower than it used to be. This is because my relationship is less linear now. That outlier is not along a straight line, so it decreased the linearity of my relationship. So let's take a look at a summary of what we just did on our calculator. The value of R does not depend on the unit of measurement for either variable. If I change from millimeters to centimeters, or I multiply or divide by a constant, my R value will not change. The value of R does not depend on which of the two variables is labeled X or which is called Y. I can change the input and the output of my data, and my R value will not change. The value of R is also non-resistant to outliers. When I have an outlier, it will greatly affect my R value. If the outlier is going to make the relationship more linear, my R value will increase. If the outlier falls away from that linear pattern, it will decrease my R value. Now, second to last thing I want to do is I want to look at the relationship between these variables for X and Y. Again, we're going to put these in our calculator, and we're going to calculate the R value between the X and Y data. And we're also, in this case, going to look at a scatter plot. So I've already got this entered in my calculator. We can do the scatter plot first. So I'm going to go to a scatter plot, and I called this on my calculator Oh, I did not enter this yet on my calculator. So I'm going to go here to a new column. We'll call this X2. And we're going to enter the data. -3, -1, 1, 3, 5, 7, 9. I'm going to go to the Y values here. I'm going to call this Y2 since I'm using the same variables. I can't call them the same thing. We are going to enter the Y values. And let's look at the relationship. So if I go to a scatter plot and I do a scatter plot of my X2, Y2 relationship, there is a very clear relationship between X and Y. There's a quadratic relationship actually between X and Y. Now let's take a look at what my R value would be. I'm going to add a normal calculator page, menu, statistics, stat calculations, linear regression, now with X2 and Y2. My R value is 0. You saw that there is an incredibly clear relationship, quadratic, between X and Y. Remember that your R value is only a measurement of the linear relationship or the linearity between the variables. While there is a very clear relationship between X and Y here, there is a very clear relationship, there is no linear relationship. So the last thing we need to note is that our value of R is a measurement of the direction and extent to which X and Y are linearly related. All right, so this last example is kind of funny, but it's really important to take a look at. We've got data here from a famous correlation study showing the number of Methodist ministers in New England and the Cuban rum imported to Boston in barrels for each of several different years. Now we know our R value does not care what we call the input and the output, so we're going to enter this in our list and spreadsheets on our calculator. We're only looking at the relationship between Methodist ministers and barrels, so we're going to enter these two columns in list and spreadsheets. Now again, I've done this for you if you don't want to take the time to enter that. So let's take a look at our data. We've got our ministers and rum data. We're going to take a look first at a scatter plot. So we're going to go data and statistics. We said ministers and the barrels of rum. Well, it looks like there is an incredibly strong positive relationship between these two variables. If we calculate our R value, if we calculate our R value, we're going to go menu, statistics, stat calculations, and linear regression. We're taking a look this time at ministers and rum. Our R value is 0.999986. So let me ask you as our final question for today. Does an increase in ministers in New England cause an increase in the consumption of rum? Or does an increase in the consumption of rum cause an increase in the number of ministers in New England? What do you think? Trick question, actually. Be very careful when you're looking at correlation. While the correlation is incredibly strong and it does show a very strong positive relationship, it does not imply causation. Correlation does not tell us that one caused the other. This is a perfect example of an observational study. Remember, we cannot prove cause and effect through an observational study. We can only prove causation through a well-controlled, well-designed experiment. Strong correlation just tells us there is a strong linear relationship. It does not imply causation. Correlation does not imply causation. Let me give you one last example of a cartoon that made this statistical mistake. This young boy is on an airplane and he says, "I wish they didn't turn on the seatbelt sign so much. Every time they do, it gets bumpy." Obviously, a common statistical mistake. Correlation does not imply causation. So please be careful when you're answering questions. We can only prove causation through a well-controlled, well-designed experiment. Have a great day. Let me know if you guys have any questions at all. Bye-bye.